video on the topic of spherical conductor. The question is from Bihar State paper. It's a old question, 2016 paper, and the topic is the capacitance of a spherical conductor. Now, as usual, what I will do is I will not give you the answer straight away. If you memorize the formulas, the answer is straightforward. But before I do this, since exams are coming, what I will do is I will do a quick revision of this topic. So let's do a quick revision of what is a capacitor, and then let's solve this problem also. I will give you a quick revision. So listen to the capacitor concepts very carefully, right? So let's start with the concept of capacitor. I will only touch upon the basic definition. If you're a student who has never studied capacitor so far and has struggled to study capacitor, you will find this very useful apart from the answer of the question. So when we talk about a capacitor, okay, a capacitor. So before we do that, let's understand that if you have a conductor, right, and you put a charge on a conductor, okay, so you put the charge on the conductor, you put charge on the conductor. What happens to the conductor? The conductor has then a constant potential on it, okay, constant potential. So if you have a conductor, you put charge on it, there is a constant potential available on the conductor, right? So you have put a charge. Now, if you pick up two conductors, okay, this was a single conductor. Let's pick up two conductors. So we will pick up two conductors, okay. What will we do? We will put charge, a positive charge on one conductor, and at a certain distance, we will put a negative charge on the other conductor, okay. These two conductors are not touching each other. So there will be a potential difference between these two conductors, right? A single conductor has a constant potential on it. If you pick up two conductors separated by some distance, then what will happen? They will generate a potential difference. All right, so what is a capacitor? This is the capacitor which I just explained you. If you have two conductors which have equal and opposite charge placed on them and they have a potential difference between them, this arrangement is called as a capacitor. That is all a capacitor is. Okay, two conductors. Now the easiest one that you study in your class is the parallel plate capacitor, where you have two conductors again. These are the two conductors, okay. They are separated by some medium. Let's say, for example, in this Bihar board question, the intermediate space between the two plates is air, right? So there is air is between them. These two conductors have charges. This has a total charge of uniformly spread charge. This also has a uniform charge all over the conductor, and there is a potential difference delta V between these two charges. Such an arrangement of two conductors having a potential difference of delta V is called a capacitor. This is a basic definition of a capacitor. Now, a lot of students therefore get confused when they get this question, which is they say, okay, you said, there is a conductor, but in this question, there is a single spherical conductor. All right. The example I gave you of parallel plate capacitor had two plates, right? It had two plates. But the question which has been asked in the Bihar board question paper is a bit different, okay? And the difference is, it says it's a spherical conductor, which means there is a single conductor. This is a case of a single conductor scenario. Now, we already know that we need two conductors to create a capacitor. Whereas for a spherical conductor, it's a case of a single conductor. So this is what we're referring to. We are saying we have a single conductor, one spherical conductor, right? So you have a single conductor, right? And question is, what is the capacitance of this spherical conductor? Now, I will clear the confusion now. See, the second conductor in these questions is considered to be at infinity. So there is definitely a second conductor, but the assumption is that that second conductor, okay, so let's draw this from, it's a concentric semiconductor. Let's say this is infinity. So that particular conductor, which is spherical again, right, is at infinity. That is our assumption actually, okay? So it is definitely there, but the distance is infinity. Just pardon my drawing because I have limited space here. So this is the second conductor. The second conductor has a radius of infinity, you can see, right? And this particular conductor has a radius of r. So though the question is that it's a spherical conductor, but remember, there is also a second conductor hypothetically, which is located at infinity. This is a major point of confusion for students. If you, on the right hand side, if you see the definition of capacitor versus what you see on the left hand side, you will see the difference that there is only a single capacitor in the question, or a spherical conductor, okay? There is a single spherical conductor situation. So even a single spherical conductor has a capacitor because the second conductor, for example, this is a second conductor, this is the first one in a parallel plate. The second conductor is also there, assumed to be at infinity. And I hope you know the formula. The formula is the capacitor is 4 pi epsilon naught R in air, right? Permittivity of the air. This is something you must understand. Epsilon naught is the permittivity. Anyway, so you can see the capacitance of a spherical conductor is proportional to radius. Okay. So remember, the capacitance of anything, be it a cylinder, be it a parallel plate capacitor like this, be it a single spherical shell, or be it a situation like this, where you have actually got two concentric shells of radius A and B. The capacitance is always, just remember that, independent of the mass of the sphere. There is no mass involvement. It is independent of volume. It is also independent of surface area. In fact, the capacitance of the capacitors is also independent of charge. It does not depend on the charge also. Now, if you say, when I say surface area, I meant in the context of sphere only. In a parallel plate capacitor, the surface area of the capacitor matters, right? So the surface area of these plates is important for a parallel plate capacitor. But in a spherical system like this, it is not important. For a sphere, it is only dependent on the radius. I hope you like this video. I have more than 100 videos on the topic of capacitor. Please do not forget to watch those 100 videos. Most of them are concepts, basics, very simply explained, and also the numericals are there. So you will get solved examples also as to how to solve the questions. This channel has 2000 videos. You are sitting at comfort of your home. What you're learning is even better than what they teach you in a classroom. Remember that. Okay. So therefore, don't forget to subscribe to this channel. And thank you very much for your time. I will come out with an excellent video again tomorrow. Do not miss it. Subscribe to this channel because this channel is giving explanation better than the classrooms. Thank you.